For those of you that are on, we'll get started in just a couple minutes. We will go ahead and get started. So thank you and welcome to this week's Purdue at Westgate webinar series. My name is Samantha Nelson and I am the program manager for the Purdue Foundry Westgate at the Westgate Academy. We at Purdue Westgate strive to promote business and talent growth, and we want to help support you as a startup, small business, and academia. We strive to be that regional hub of connection and support. Purdue at Westgate is located within the Westgate Academy. The Westgate Academy is a technology incubator, training, and office conference center. We are located within the Westgate at Crane Technology Park, which is directly outside of the Naval Support Activity Center in Crane, Indiana. We would like to thank our sponsor and presenter for this webinar, CACI International. CACI International is an American multinational professional services and informational technology company headquartered in Arlington, Virginia. They provide services to many branches of the U.S. federal government, including defense, homeland security, intelligence, and healthcare. We are excited to have a satellite office of CACI within the Westgate at Crane Technology Park, supporting the Naval Support Weapons Center in Crane. Today, we are excited to be hosting a webinar with Rick McGinley. Rick is the RF Systems Design Engineer and System Architect for CACI out of the San Antonio, Texas office. He will be speaking on additive manufacturing for military and commercial radar enclosures. We ask that you mute your microphones, and if comfortable, you can leave your video cameras on during the presentation. Please feel free to use the chat function at the bottom of your screen to ask questions, and Rick will answer these following the presentation as much as he can. The presentation and recording of this webinar will be sent to you via email prior or after the event, after the webinar. So stay tuned for that. So again, thank you, Rick, for joining us and being able to speak on this topic, and I'll hand it over to you.
All right, thank you, Samantha. Let me get right to sharing my content here, screen. All right, folks. Today, as the title suggests, we're talking about additive manufacturing for military and commercial radar enclosures. And you'll soon find that this definition of enclosures gets expanded very quickly. But today I want to talk about the technology more from an application standpoint and less about how do we do 3D printing or additive manufacturing. And we'll see as we go along where there's plenty of opportunities here for collaborative efforts, cooperative efforts, and partnering. Okay, on our agenda today, I will talk a little bit about some of the definitions I just explained that we're going to go beyond enclosures. So that'll be important to establish that here soon. So we'll be talking about some of the key materials some methodologies, in other words, printing types, printer types and processes, and some examples. Now, the examples are taken generally from both military and commercial applications. They apply equally well to both civilian, commercial, or military applications. And a lot of this stems directly from simulation-based design, where we're actually big on that as a company. And so one of the things that we try to do is model first, from the model, tweak the expected performance, create a prototype, if you will, a rapid prototype, and then we begin testing it for comparison with the model, and then from there we would go to either limited production or a full manufacturing scenario with the output of that. And many of you have been around for a while know that in the old days, modeling simulation was for insight, not for numbers. And some of the tools we're going to talk about today pretty much put you in a position where if you can model it and evaluate it, you can build it. So we'll keep that in mind, that it's a capability that I know a lot of you out there have access to or are using now. And what we're talking about today in applying additive manufacturing to this modeling process, it actually gives you a kind of a heads up, if you will, on being able to cut down on your purchasing time, acquisition time, and reduce material shortages quickly. So we transition over to our definitions, and I realize that enclosures mean different things to different people, but today I'm going to loosen it up a little bit, and I'm going to talk about enclosures being boxes, if you will, EMI, RFI, or electromagnetic or RF radio frequency interference reduction enclosures, like a sensitive radio receiver or radar receiver might be put in to keep the outside world from interfering with it. And RF and microwave components, which you certainly use a lot of those in radars, and those would include antennas, some fairly complicated complex ones as well, filters, array elements, radomes, and support equipment for antenna interface. Now, on the support equipment, I think the discussion we're having today, we'll talk about different materials that we can print. One point that I want to leave you with is, I know for military hardware, you really can't introduce it into the inventory for general use or operational use until it's been through some environmental stress screening. Now, different services call that process different things, but in our case, for discussion purposes, I'm going to call the process of qualifying a piece of equipment or hardware or component as a environmental stress screening process. So this, the technology we're talking about today is capable of building hardware that can pass all of those environmental requirements. So I'm not trying to suggest that additive manufacturing or 3D printing is a way to skirt around the mil spec requirements. We certainly respect the very reason and the logic behind having those. And also for today, some of our reference material, most of our reference material came from the IEEE Explore site, where it came from vetted sources and vetted processes, and some of the organizations that put out the material are renowned for their work and their accomplishments in this field. So I think without any further ado, we'll get into starting off with a discussion on some of the materials. So 3D printing goes beyond plastics and beyond the injection molded stuff that you make, smaller devices that are made out of plastic materials. We can, the industry has been able to print metal materials and precious metals for a long time now. These include some of the things you see here on the list. Aluminum is an important element for us in prototyping some things and making chassis as well, especially for EMI, RFI, and other electromagnetic interference controlling devices. Precious metals, obviously, gold and silver come to mind on that one. Stainless steel, tool steel. All of these materials are now in a form where they can be printed with the right device. Again, I'll mention that today we're talking about the applications of these as opposed to the physical description of how it's done. In the end of this presentation, or certainly as a result of giving it, I would hope to be able to discuss with you some of your own capabilities and anticipation and maybe teaming up in the future to take advantage of capabilities that you have and capabilities that we have. So as you know, it's easy to say this is possible to build this prototypes and limited production articles, first articles, if you will, via this additive manufacturing process. But some of the tooling obviously requires a investment of capital equipment. And so what we're trying to do today is talk a little bit about the capability that we see that we're exploiting to bring to the market for technology insertion, and also to try to figure out what's the next step in terms of how do we grow this to meet current needs. So, and that's always the case because we all work in an industry that is heavily requirements driven. Beyond metals, plastics, dielectric materials, dielectric foam materials for radomes. There's some examples of material that have been used successfully for radomes. Now, radomes are not a pet project with me. I just am completing this week a project to test a radome for high performance fighter aircraft. So we didn't make the radome, but we tested it. We built a system to test that. So what's important here is to know that in the case of, say, for example, a fighter aircraft, you're not going to get much choice in how the radome is designed, but you will get to determine whether or not it meets the original operational requirements. So in some cases where you have an opportunity to either start from scratch, either as a new development or a sustainment initiative to replace a radome, for example, these are some of the materials here that you see that are commonly used for radomes. And later on, I'm going to show you some specific examples of how some of this material has been used. A little bit about the characteristics. Now, this is obviously a long ways from a full material data sheet or a data sheet on the material itself, but within a short abbreviated form, each one has its own strengths and weaknesses. Some of the ones here that have very good strength, rigidity when they're in the finished form are also not as good on the dielectric properties for making a radome, but they will survive in a really rugged, high speed, high temperature environment. So everything, as you know, is a trade in some way in designing radomes. But probably the most useful material that I've seen in quite a while that comes out of a 3D printing process is the glass reinforced plastic, glass fiber reinforced plastic, the styroderm foam material here. It has really good dielectric properties and temperature. In CACI, in the group that I'm with in San Antonio, we do have a Mark IV X7 Gen 2 printer that we've used for supporting at least one radome test project. And in the future, we are going to expand the use of that to build up actually radome samples to test dielectric constants and the S parameters that you see there, the scattering parameters, the reflectivity, transmissivity, loss tangent. These are standard parameters you test at a radome that give you a good clue as to how the radar is going to perform behind it. So that's where we're going with this thing in the future. In the future uses, I think will be good for us, for our applications in San Antonio, is some of the brackets and tools and fixturing we've had to incorporate it into the test system that are simply not available via other means. So if we couldn't print them, we would have to resort to the old-fashioned way of drawing the part up and sending it out for bids to get it manufactured, and that costs us time and effort. So some of the printing processes for both plastics and metals that you see, and some of you may already be doing this. The direct metal laser sintering process is one that I hope we can get into even further at CACI. But right now we have a limited capability, but we are using it to expand the parts manufacturing process for the radome test system that we have. So that'll be a little clearer later on when I get to discussing that particular example. And stereolithography is always it's fairly popular. It does work with both metals and plastic materials. And it's probably most known, as you see there, for resin 3D printing. And some of these are used for making molds and other things that where other materials are injected into them. So each one of these technologies that you see has a place in the industry and a cost associated with it to kind of bed down that capability in a lab someplace. You pretty much have to be looking to solve some current problems and identify a path to get to future requirements as well, because some of these printers to print large objects take up a lot of room. But going back up to one bullet to the laser sintering process, as you see there, stainless steel, aluminum, and other high performance alloys are products that can come out of that. And a little bit about that process, it does use a high power laser to sinter the small particles of polymer powder and or metal, for that matter, into the shape, ultimately into the shape. So we have made a few EMI RFI enclosures around a radar receiver, and that has saved us a lot of space in there, because where we would normally run semi-rigid RF cabling, we were able to use a circuit board and build RF or EMI RFI pathways inside of the chassis that help reduce noise. That was a big boost to our RF capability and being able to field a system recently that I'll discuss here later. And then the FDM process, the fused deposition, is another technology that is fairly common in higher end facilities. And the thing that, as the bullet indicates there, the materials, the plastics, and so forth that you can use do result in very accurate replication of the part that you're trying to copy. It's strong, durable, stable in terms of dimensions. And we believe that particular technology for some parts will be able to breeze through I won't say breeze through, but I will say meet military specifications, in which case we'll be looking in the future to have a way to do accelerated life testing on some of these parts to maybe speed up that process even further. Okay, going to our first example here. If I could call your attention to the pictures on the right-hand side of the slide there. This is a slotted waveguide array antenna that was made. That thing, the entire thing was printed. There's a process, electroplating process, one of many processes used to coat the inside of the waveguide. That's a fairly straightforward process for lower band radars. You get up into millimeter wave, and then you have to be careful of what they call the surface roughness of the plating on the inside. It can generate some issues, but in every case, you can evaluate these assemblies fairly easily. And so one of the reasons why I included this example is because it is the entire class of examples I'm going to show, I consider to be most important, at least within the radar industry, because of the alternatives. Sometimes it's difficult to get array antennas made, and certainly there's always a lead time issue with it. So I won't tell you that it's an easy task to just say, I'll just print this in my own lab, but I will tell you that with some level of organic capability, I think you can streamline that process. And what the graphic below is showing is that starting with a model and following through the model and then fabrication process, the real hardware that gets printed matches pretty closely the model, and it can be used to synthesize an antenna pattern. So let's say you have a legacy system that has a slotted waveguide array as an antenna, and the vendor's gone out of business, and it's been years since you had to make one of those parts. There's an excellent chance that you could do a 3D print scenario on that, knowing something about the antenna patterns that you're trying to synthesize. And with that, you would use, I've listed 3 computer aided engineering tools there, both MATLAB and CST Microwave Studio and ANSYS HFSS Studio. Those are good. I'm not selling those products today. I'll just tell you that each one of them is capable of handling the task of designing an antenna, modeling its performance, coming up with the critical parameters, and then ultimately that could lead to a 3D printed version of it. I will say from personal experience that MATLAB set of tools gives you a lot of flexibility for other analysis tasks beyond just doing antenna design. So I tend to lean to that tool as the go-to design aid. But the major advantage, I think, to printing an array like this is, one, it very closely maps the model or the design antenna that you have created using one of these tools, and it's easy to validate that with a vector network analyzer and a reasonable amount of or an anechoic chamber access to do some antenna testing. I think what you find is that not only are the patterns accurate, they also the array itself will handle the power levels and things like that that are common in a lot of transmitter arrays and receive channels. So this, I mentioned before, it cuts down on the development time. And so, we tend to think of this technology as supporting new development efforts, and yet the vast majority, well, I don't know if I want to say vast majority, but a significant percentage of the workload faced by the military today is sustainment initiatives against systems that have been in the field. So that's where the headaches began, trying to reconstruct something that was made a long time ago, but is still in service. So I believe not only can you meet this same performance expectations and specifications that the original part had, but you also have a way to cut down that lead time and actually bring this process in-house. You can, the process for creating an article like this does lend itself to a rapid prototyping initiative, where you start with a simple set of requirements to work through a model. From a model, you do a first article or a prototype and evaluate that, and what comes out of the end of it is a model that gets updated by measurement data and a final product that can go into manufacture. The other thing about these array antennas that I've experienced personally with a lot of systems over the years is hardware in the loop testing, system integration lab testing, where maybe you have an entire system, which might include a radar, the transmit stage, the receive stage, signal processing, display, communications. All of those capabilities are put into a lab for evaluating performance issues or doing software development or even replacement hardware development. The good news is that printing some of your materials, like an array antenna, for example, gives you a way to operate this lab where it may be difficult to get an operational asset. And so what am I talking about here? I'm talking about the folks that build hardware in the loop testing for actual aircraft systems, for example, or ground-based systems for that matter, where they have a need to put as much of the operational hardware in the loop as possible. And yet the actual hardware is difficult to get because of operational requirements. So it's one thing to have a fully operational fleet of aircraft or ships or whatever system subsystem that you are working with, but you often find that you just don't have the spare assets available to build a full up hardware in the loop test system for those systems that are already fielded. If it's a new development item, it's a little different story. So our approach here is that by building for example, I've chosen this array. By building that and testing it against the legacy articles antenna patterns, you find you get a good match. And for purposes of doing software development for signal processors or detection processing, it may save the day for you. It may help you be able to implement the lab that you need to build or sustain and still be close enough to the real performance of the actual hardware to be usable. The second one is an example here of another slotted waveguide array antenna that uses frequency scanning, and it has a built-in power divider. So if I can focus your attention on the picture over there on the right-hand side above the synthesized word there, you see the shape of the slots, if you will, in the waveguide in the center of it. And you'll see beneath that is the flip side of that unit. Well, this particular article was printed directly, and it was silver plated on the inside, and with this coating process, was able to get keep the losses down, and all the S parameters look really good with that one. And the B side of this picture, those slots are cut in there a little differently to facilitate the electroplating process, because those are non-radiating slots, and so that's one of the things that you can do to facilitate building this thing. Now, obviously, if you're a mechanical engineer and you've got a 3D SolidWorks model of something that you want to build and you want to send it off to the printer, one of the first things you have to be concerned with is okay, how the heck do I print this thing, and how's the machine going to respond to the file, and how does it get assembled? So the plating process that goes on inside, it obviously requires some access to it, or you have to build it in parts that can be put together. So I think in this case, with this particular slotted waveguide, they were able to build it by gaining access to the inside through the non-radiating slots. And I think what's important here is the antenna patterns on the bottom. This particular array was intended for a scanning application where you feed it with different signals, and you can see the angular offset there that as it passes through the array. Also, you can see that from the return loss standpoint, the reflection coefficient, it is pretty well optimized for the original specification that they had. The pattern information up in the upper left-hand corner is a result of the modeled effort. And when you get down to the measured and evaluated effort, if you can change the aspect of the profiles and show a true apples and apples comparison, that the model does very closely match the evaluated piece of hardware. And that, to me, that's kind of significant, because there's a lot of times when you may want to or have to build an antenna like that, whereas you can't get the original hardware to use to lend the realism to your test system. Another very important class of RF waveguide materials for both radar and communication systems is waveguide filters that you see on this slide right here. This particular one was a millimeter wave. The thing that's kind of important about that is, again, it takes advantage of the non-radiating slots to plate the inside of it. And the filter characteristics itself are almost textbook. And when you use the filter design tools at either MATLAB or CST suite, what you get is plots, if you will, performance plots that very closely match the measured values. And so with most of these parts like this, the two primary parameters you're concerned with are the reflection coefficient and then the forward transmission S parameters. Those are very important parameters. And I think this particular effort was the scientists and engineers that worked on that, they're very pleased with their results. And so waveguide filters, they're very useful and kind of life-saving in some cases, because you may find with certain systems, whether they be commercial or military, that you are operating in a new area where you're getting interference or you are causing interference, and you may need to quickly adapt and use a waveguide filter to get rid of components that are being transmitted. So being able to build one of these things up from a quick design to a quick model, a prototype, and a test is a big operational plus. And the modeling effort, as the plots show, run very close to the physical hardware, so that does save time. And so that's important. And the CAD tools that you would use to design that filter are they're I won't say totally open source, but you can buy them right off the shelf and apply them. There's nothing custom about that software. It's just how you use it and for your own design requirements. And these waveguide filters, they do have a very good power handling capabilities. There are some precautions with some 3D printed materials where temperature is an issue. But again, between selecting the materials and selecting the plating inside, you can overcome most of those. And as I alluded to earlier, if you can have a way to do an accelerated life test on a part, halt test as it's referred to, where you can stress the part at a much faster rate than it would experience in real life, then that would certainly give you some insight as to the survivability of the part. And again, I think coming up with a credible way to certify the environmental quality of the part itself would be imperative to being able to use it in military hardware and in a lot of commercial applications as well, where reliability is always going to be key. I want to go back to one slide here. One point that I forgot to make on the modeling effort for this particular slotted waveguide array, of the tools that I mentioned before, each one of them has a way to basically take a template, if you will, for a specific antenna type. And it allows you to say, okay, I want a slotted waveguide array. I want it to have so many slots in it. In this case, the one that you see here has 18 slots in it. You want it to pass a certain band. You want it to have a certain bandwidth, and the parameters that you can control within the model obviously include the slot width and the slot spacing, and the longitudinal distance between the slots. Those are all important, and the slot spacing generally helps with the phasing between the radiating elements. So you can see in the final pattern the effect of that. And normally there's a whole, the tools that you're using to design this give you a way to say, okay, what is the free space wavelength? And then you calculate the wavelength that goes on inside of the waveguide, and then calculate the slot spacing and width. And so, and from those parameters, the slot width is generally helps you control or adjust the overall bandwidth of the antenna. And I know in many applications you'll see slotted waveguides where the slots are on the narrow side. And from a modeling standpoint, you get about the same antenna patterns, but the slots in the narrow wall of the waveguide assembly generally give you a little bit wider bandwidth on the overall antenna. While the patterns look very similar, the bandwidth of the antenna can be a little bit greater. And so all of those things can be modeled and then printed. So I can't make that point strongly enough, because it does give you a lot of flexibility. Okay, now this one here is, I know some of you are probably familiar with the active electronically scanned arrays, kind of the newest technology in radar antenna design. It's very important for a lot of reasons, including the fact that it doesn't have any moving parts. It's very, very reliable, and you can, it facilitates, I'll just say, multiple object tracking. So you can use a phased array radar, an AESA radar is just referred to, for a lot of high performance radar applications with different modes of operations and different functions. Can't get too far into the details on that one, but I will tell you that most modern radars of this type, the strategy was, because of their reliability, they're designed to be part of the airframe. And I'm talking obviously aircraft installed parts now. The reliability is, it's not unreasonable to expect that array to last the life of the airframe. So a couple of things about that. The folks that make those kind of antennas, arrays, are going to take advantage of that, because they can hold the line on cost, because they don't necessarily need to have a lot of expensive spares in the inventory. But it will make it more challenging for you if you are attempting to build a test system, which we'll talk a little bit more about in some coming up slides. What this particular experiment showed was that it is possible to do a 3D print of the individual array elements. And those arrays, if you see, there's two different types that were printed there. They produce the patterns that you see. Now, if you have a reasonable amount of experience with phased array antennas, electronically scanned antennas, you'll know that those patterns look like, you could do a lot better than that. There's a lot of grading lobes and a lot of artifacts in there that are the result of the manufacturing process, or not optimizing the elements for a specific application. Now, the folks that did this work, they admitted that right up front. Their intent was to see whether it was possible to even print a use array. And quite honestly, the answer to that is yes. But I think, as they so aptly pointed out in their research, was that you need to keep it focused on a specific application so that you get the spacing correct, the shape of the subarray elements is correct to eliminate the grading lobes, and a lot of that is controlled by the spacing of the slots in there. And so it depends on the application of it. In some cases, the grading lobes actually are used for gaining certain information out of the radar that you would normally not get from just suppressing the grading lobe and just using the main beam. Since we are talking about printing this stuff and not necessarily about a radar tutorial, I'll just say that it is possible to control the assembly and printing of these array elements to give you the pattern that you're looking for. And again, I make the same point. The reason that you would do this is because you ultimately have a system to sustain and support and sustain. And again, a lot of your test systems are going to require that you have an antenna built into the test capability, especially if you're testing radomes that go over this particular radar. And yet, the idea of having a aircraft part in your test system, it would be great to do that in some cases, but you may never get there. You may only have the opportunity to do a reasonable facsimile of it, and if you can match the antenna patterns, then for all intents and purposes, you can do a radome evaluation on your test system using a 3D printed array. And then the second reason for doing this is a lot of this type of radar technology can be applied to UAVs and expendables. I'll leave it at that. The thing that's important there is that it's fairly low cost and lightweight. And when you've got a UAV or a drone that you want to have an advanced capability, radar detection, processing capability, it would be great if you could use this technology to build up some of the critical materials and save weight on the structure. So the additive manufacturing process in this case does pave the way for lower cost use of radars. And that also by virtue of the technology, it also applies to even some 5G applications, just based on how the beam steering is accomplished. So what they did in this case, in the article that's referenced there, it's on IEEE Explore, is they built up a single array, a single element, had 2 slots, and they tested that, and they tested it from both the E field and the H field evaluation, and then they put them together in different array shapes. And we talked before about linear arrays versus linear and rectangular arrays, and the circular array that you see here is really just kind of a special case of gathering a group, if you will, of custom tailored linear arrays put together and connected together in the plumbing in the back. So I think that this particular technology holds the most promise for supporting modern advanced generation radars that are going to be lightweight, easy to carry on UAVs and drones and all. And the application for that is it goes well beyond military applications. Obviously, there's environmental studies. There are geodetic surveying. There's LiDAR applications, for example, for the Forestry Service. There's all types of reasons why this type of new technology will be applied to lightweight aircraft systems, and being able to sustain that or actually fabricate it is key in my opinion. The next example is the one that I alluded to before. This is the system we're currently in the process of fielding. We expect the acceptance testing of it is done. We're going to have a sign off on it by the 9th of March. We'll go into training with the customer's technicians next week, and it's been a big relief for us to be able to deliver the materials that we needed as a result of 3D printing, because we had no other way to do it. Now, I'm going to take you through this a little bit, because it's kind of an important distinction here. What you're looking at is a way to test a high-speed, high-performance aircraft radome. You can see from the pictures on the right, the upper right quadrant there, that the radome is mated up over the antenna and mated to a bracket, and from there, that thing gets mounted on this test system. Okay, this is a legacy aircraft. There's not a lot. There's not in generally from the model that we're talking about, it's not in production. So there are a finite amount of spares in the field that logistics channels are constantly making sure that those assets get repaired and returned to the field for use. And so when you're talking to them about building up a test capability, and you tell them, well, I need a radome and I need an actual aircraft antenna, it's easy to understand the frustration that you see when they say, well, it's great to have that capability in our test system, but we just can't support it. In this case, we got lucky. They did support us with an antenna, so we're using the actual antenna in this radome evaluation system. And since the very purpose of the system is to evaluate radomes, we had plenty of radomes available that had to be tested in a depot environment. The challenge was, one, mounting the antenna on the structure in the same configuration it was mounted on the aircraft, on the airframe, the bulkhead, and then putting the radome over that with the same hinging and so forth as it has on the aircraft. Even hinges, even brackets and mounting fixtures are scarce. They're very difficult to get. So we wound up, from the drawings we were able to get from the customer, reconstructing those articles and printing them. And when we mounted that thing together, that radome, when it closes over the antenna, for all intents and purposes, it is just like it's mounted on the aircraft. It fits the same way. The radar antenna operates the same way inside that radome, and we're able to evaluate its performance over different azimuth angles and scan angles of the radar itself, or the radome. Because in the case of measuring a radome for a tracking radar like that, you actually have to establish an RF track loop so that the antenna can be free to track a source, and the radome can actually move around that point. And that's one of the ways that you have of measuring kind of an important parameter in radomes for radars like that. Excuse me, is the beam deflection error. And there's a lot of mechanics to that and a lot of electronics, but the point is the realism that the customer wanted to maintain in that system could not have been achieved without us using a 3D print scenario to build the critical pieces that we had, because they were otherwise not available. And this is a measurement system that is fashioned after a hardware and a loop capability. And what we were able to build for them was literally flight-worthy structural components that helped us mate the radome and the antenna to the positioner system, and then run a series of tests on it. And the advantage that you get with that, by keeping it as close to the real world application, is that we were able to take advantage of the radar's inherent azimuth and elevation accuracy, because beam deflection error is a very small number for this particular system. And to be able to measure that, it takes quite a bit of precision in your measurements and motion, if you will, to be able to characterize that. And now it is one of the most important measurements that can be made for fighter aircraft, especially. So that's how we applied that. Now, I mentioned before about printing the AESA antenna, AESA elements. And now with respect to this particular test system, this has to be modernized. This particular configuration supports the sustainment of the current fleet of aircraft, but that current fleet is going to be upgraded, and it's going to include an AESA radar, whereas the radar that I just showed you is electromechanically scanned. The antenna scans in azimuth and elevation, and then it's like a standard legacy fire control radar from there. In the new versions of it, it is an agile electronically scanned array. So my hope is that we're able to print that antenna or print that array, because it's unlikely that we'll ever see an actual piece of hardware that we can use on this tester, because of its cost for one thing and the availability for another. It'll be several years before we could provide that test capability. But I'm holding out hope here that through some experimentation and research and what others have done, is that we can build a reasonable AESA array to use for evaluating antenna patterns or the radome material itself. So what will happen with our test system is we'll kind of turn up the gain on it a little bit, and we'll use additive manufacturing to produce an array that is equivalent to the actual radar array for purposes of testing the radome. And that's what our objective is, and that's what we're working towards right now. I've generated several white papers on how we would do that. And I always caveat that by saying, if you can give me the array, we can work with it. But I think what's going to happen is we're just going to be delayed in putting the new test capability out there until that array is available, or else we would make a bold effort to try to print something that represents a reasonable facsimile. Here's a commercial system that might look familiar to you in some ways. I will say that the challenge here was to provide both S-band and C-band for maritime surveillance, used primarily for rescue efforts. The thing that's interesting about this is, if I could call your attention to the antenna array on the left-hand side, the rectangular housing that I've tagged over there, if you were to pull that radome off, what you'd see underneath there is the 3D slotted array antenna. Now, this is obviously a simple system because it doesn't, like a lot of military systems, it doesn't have the secondary radar attached to it, the secondary surveillance radar, IFF, if you will. But it does have the dual bands. And so this was a tactical demonstrator system, and it had to meet a lot of fairly ruggedized requirements, not the least of which was rotational stability, environmental protection from the elements, and the antenna array had to be fairly lightweight. So they made that, the blue part of that thing, turquoise color, is this styrodur foam material. It's a rigid foam, really good dielectric properties. And they mated it to the surface, the front surface of that rectangular housing. So what's interesting about that is that there's a couple of ways that you can do that. One is you can kind of build a mold for it. Number two, you could take the radome off, do a 3D detailed high resolution 3D scan and build a model to make a mold, if you will, to make that piece up. But it does provide some very nice rigidity and environmental protection for the array itself. And as you can see on the right-hand side, the antenna patterns for the two bands, S-band, C-band, and the artifacts that are generated there in the blue color right over here, these are things that can be controlled somewhat through the design of the array, but they're down, as you can see, they're down quite a ways, 30 dB or so. So they're generally not an issue, and the first side lobes here are well within specification. The thing about slotted array antennas, like a lot of antennas, they have standard 13 dB side lobes without putting some tailoring on the array. But in this case, the antenna performance behind that radome is excellent. And so I think therein lies another application for being able to print a radome of that size. One of the things that I'm looking at is being able to print that in, say, multiple pieces and assembling it to still give us the same rigidity, but making it easier to print, because that particular array is 10 feet wide. So that makes a manufacturing process a little challenging, but it can be done, and obviously they did it here, and they got some really good results. So we have high expectations that we can work out a 3D printing process to manufacture a radome that looks like that gives us the performance and survivability we need in a marine environment, and still be able to hold the cost down on that. So that was a good initiative on their part. Again, I went to the IEEE Explore site, and I looked at that because it's a wealth of knowledge in terms of who's doing what, and this particular system has so much application to other marine uses. Okay, we've kind of reached the point where I want to summarize a little bit. These things tend to go a little bit faster when we're not doing questions in real time. So let me just summarize this one. I think what we've talked about today is additive manufacturing. I've used the term 3D printing interchangeably, and it's obviously key to rapid prototyping. I mentioned that it can shorten up your development cycles, and it can be used to make lower cost, lightweight radar components, subsystems, enclosures. We're still doing that on this test system for the radome, because we've made several chassis that we've been able to reduce the noise and the background noise and noise figure in the system by controlling the outside world contribution. 3D printing is obviously supported by a simulation-based design process, and if you're a process improvement type person, or that's what your task is, I'm sure you can visualize a simpler model to follow for rapid prototyping. It just starts, as we alluded to before, with a specification sheet, a model, an evaluation of the model, if you will, an assessment as to whether or not you want to go to printing, and then any printing and evaluation criteria or measurements that you take get fed back into the model, and then ultimately that reduces to about a 3 or 4 block process, which is manageable. Both the metals and plastics, including the rigid dielectric materials, and some for high temperature, high performance environments like radomes on fighter aircraft. I personally would not attempt to print one of those myself, but I certainly recognize that the because of the structural design of those things, if you find anomalies in the dielectric coefficient on the material that is affecting the beam deflection angle, the only thing you can do is add dielectric tape to the inside of the radome. And so that's it's kind of key to be able to test a radome for fire control applications and be able to come up with the right application of the tape. And so I also believe that providing a way to evaluate the insertion phase delay on a radome where the antenna is fixed behind it and actually provide some tailoring, if you will, some tapering within the dielectric material itself to smooth out the patterns is a possibility. So continuing with our summary here, EMI, RFI enclosures, all slotted waveguides are their priorities for us because of the direction we're going with this test system. And this is becoming a bit of a product line for us where we are now on contract to build a third unit. And you know, it's always about process improvement and things that we see that could be done a little bit differently to save money and make things more efficient. And so the additive manufacturing process is the thing that's paid us the most dividends, and that's why we've put it way up high on our priority list of how to apply a technology, a different type of technology for insertion initiatives that can ultimately help your customer. So, and we just talked about the fact that the workflow itself lends itself to simulation-based design. And the thing that I'll tell you about that is it can help bring work back in-house. Okay, put it under one roof, where you can literally have the design and simulation and synthesis process in one building. You may find that it's better to engage certain team members that have printing capability for specialized pieces, but it simplifies and streamlines your process when you can take to them a set of files that represents a finished product. And so I believe there's a lot to be said for that, where you can take ownership of your own design and then get it printed and buy that as a service. And ultimately what we're trying to do is to cultivate that capability in several areas around the country so that we can go there and get work done with a high expectation that it's going to be a much simplified workflow. So I have said my piece here today. I guess I should open it up for questions now.
Yeah, Rick, there is quite a few questions actually. And okay. So for the sake of time, I just wonder if we should take those offline and I can provide you with those questions and you can answer them directly.
I think that's
You think that's a good idea?
Yeah, it's a good idea.
Okay. Okay. Yeah, I think because there's a couple of them that are pretty in depth, and I think it would be best. And we just for the sake of time, we've lost a few people, not many, but we've lost a few people. So okay. So we've definitely had a great participation today. So we're happy that you were able to do this for us, Rick. So we'd like to thank you for joining us today, all of you, including Rick and all of the CACI team, and for sharing with us your expertise on additive manufacturing on radar enclosures. I'm sure that Rick will be more than happy to answer your questions at any point in time. Within our presentation and recording, I will also provide you Rick's email address and information so that you can directly ask him questions. I do realize that there are several questions. So like I had said, we will also provide Rick with these questions and your email addresses so that he can answer those directly for you. So again, we want to thank CACI for not only presenting on this webinar, but also for sponsoring it. So we have a lot of other webinars coming up, a lot of information. We would like for you to check out our website at www.westgateacademy westgate-academy.com. If you click on a tab there that says Purdue at Westgate webinar series, you'll be able to see a few that we have upcoming. Also, if you want to learn more about any way we can support you, whether it be co-working space, conference or office space, or even just helping cultivating an idea with your startup, certainly check us out on the website and check out our future events. So we hope you enjoyed today. I know it was a lot of information. Rick is obviously a perfect subject matter expert on this, so we really appreciate him providing this information. So hopefully we'll be able to meet each one of you in person at some other point in time. So in the near future, I hope. So everyone have a great rest of the week, and hopefully we'll talk to you soon. Thank you.
All right. Thank you, Samantha.